Swayamprabha. Digital India. Educated India.
In our previous lecture, we discussed about the various conservation principles, and let us briefly recapitulate what we discussed. So, we started with the Reynolds transport theorem, then we first derived the Reynolds transport theorem. I am just recapitulating what we have done, so we will not get into the details. So, in the Reynolds transport theorem, what we essentially did is we expressed the change in the system in terms of change in the control volume. We applied the Reynolds transport theorem to the principle of conservation of mass, that gave rise to the continuity equation. Then we started considering the Reynolds transport theorem for momentum conservation and typically linear momentum conservation. So, we have not entered into the linear momentum conservation as yet, but we tried to basically express various forces acting on the control volume. So, we tried to express the forces in terms of the surface force and the body force. So, we defined what is the traction vector, and we express the traction vector in terms of the various stress tensor components by using the Cauchy's theorem. So, that is what we did, and we will take it up from there. So, it is important to understand that we are going to apply the conservation of linear momentum as by expressing the change of momentum in the rate of change of linear momentum for the system by relating that for the system with that for the control volume. Once we do that, a question remains that what happens with the angular momentum, because when we write the equations of conservation, very common equation that we write is equation of linear momentum conservation. Where does or where goes the consideration for angular momentum conservation? So, we will consider that in a moment. So, if you look here, you will see that we are considering a rectangular element. In the rectangular element, the dimensions along x and y are delta x and delta y, and what we are trying to see is a basically rotation of a 2-dimensional element. So, the 2-dimensional element is in the xy plane, and we are interested to characterize the rotation of this element with respect to the z axis. So, when we want to do that, we will express various forces acting on the element. So, what are the forces acting on the element? The forces acting on the element are surface forces and body forces. This is not a complete free body diagram. We have not shown the body force simply because we want to find out the moment of all forces with respect to the center of mass of this element, and because the body force will pass through the center of mass in this particular case, it does not have any net moment with respect to the center of mass. So, therefore, if we consider an axis, a centroidal axis, which is basically coincident with the center of mass in this case, because it is considered to be a homogeneous body. So, this may be considered as an element of fluid or an element of solid. So far we have not distinguished between fluid and solid. So, let us try to identify various surface forces. We have already discussed that the body force has no contribution towards creating a net moment with respect to the centroidal axis, but surface forces will have. So, what are the surface forces? So, if you consider the right surface, for example, you have a normal stress which is tau 11. The first index, just for recapitulation, first index is the direction normal of the surface. So, tau 11 here means that the direction normal of the surface is 1, that is x1 direction or x direction, and the second index 1 indicates that the force itself is along x1 direction. So, this is tau 11 is force per unit area. So, the total force is tau 11 times the area is delta y times the unit width along the z axis. So, tau 11 into delta y into 1. Similarly, you have the shear stress which is tau 12, the first index 1 for the direction normal along x1, the second index 2 for the force itself being directed, sorry I will put the cursor properly, the force itself being directed along the x2 direction. So, that makes it tau 12. So, tau 12 into delta y. So, similarly on the opposite face you will see similar expressions like tau 11, tau 12, only they are all in the negative x1 and negative x2 direction. The reason is that the outward normal to the left face is actually minus x1, not plus x1. So, similarly we consider the upper face the normal stress is tau 22 and the shear component of stress is tau 21, and the lower face the normal component is tau 22 and the shear is tau 21, same thing, but their positive senses are just opposite because their direction normals, one is positive x2 and another is negative x2. So, now we are interested to know what is the net moment because of with respect to the centroidal axis of the element. So, the net moment usually if you see here, the moment is contributed by the forces tau 12 into delta y and tau 12 into delta y, they are acting in the anti-parallel direction. So, they are giving rise to a couple moment. So, the couple moment is given by tau 12 into delta y times the distance between these two forces, that is a couple arm, that is delta x. So, tau 12 into delta y into delta x, and this is a anti-clockwise moment. So, we consider the anti-clockwise moment to be positive. Then the tau 21 into delta x on the upper face and tau 21 into delta x in the negative x direction in the lower face, that will form another couple moment. So, that is tau 21 into delta x times the distance between these two forces, that is delta y. So, this is acting in the clockwise direction, because this is acting in the clockwise direction it is negative. So, minus tau 21 into delta x into delta y. So, this is the net couple moment. The normal stresses tau 11, tau 22, these all these forces due to these stresses will pass through the centroidal axis and therefore will not give rise to any couple moment. So, net couple moment is the moment of inertia with respect to the same centroidal axis times the angular acceleration. Okay. So, the moment of inertia is proportional to the mass, which is rho into delta x into delta y, that is the into 1 is the width, that is the mass, into delta x square plus delta y square into some constant. That constant for a rectangular element is 1 by 12, but I mean let us not so much bother about the constant, some constant say k into delta x square plus delta y square times the angular acceleration alpha. Okay. Now, if we take the limit as delta x delta y tends to 0, see you look at this expression carefully, in both sides if delta x delta y tends to 0, delta x into delta y will be cancelled, because they are tending to 0, they are not equal to 0. So, you can cancel that from both sides, and then in addition in the right hand side you can substitute delta x and delta y both as tending to 0 in the limit. So, you will get tau 12 equal to tau 21. So, we can generalize that by considering all possible rotations and write tau ij is equal to tau ji. So, we write this expression not explicitly in the equation of motion that we usually describe, but we write it implicitly, because in the Cauchy's theorem when we write T is equal to tau ji into nj or tau ji into eta j, if you consider the previous slide. So, T is equal to tau ji into eta j, this is what we had derived in the previous lecture. Now, we will substitute in place of tau ji, we will write tau ij. So, we will write T with the ith component of T basically is equal to tau ij into eta j. Remember that because j is a repeated variable, there is a summation over j from j is equal to 1 to 3. So, eta 1 is the x component of the unit normal vector of the surface, eta 2 is the y component and eta 3 is the z component. Okay. So, to summarize the contribution of angular momentum, we are not writing an explicit separate equation for angular momentum in terms of differential equation, but in the differential equation of linear momentum we are going to substitute tau ij equal to tau ji, that is where we are incorporating the consideration for angular momentum. Now, a very important question, is tau ji equal to tau ij always valid? Now, this is a very critical question, because see, while deriving this tau ij equal to tau ji, we considered a body force but no body couple. Okay. So, no, there is, even if we consider a body force, the body force will not give rise to a net moment with respect to the centroidal axis, but if you have a body couple, that is some couple which is acting over the entire volume of the body, then that will give rise to a moment, a couple moment, and that moment should add to this. Therefore, in presence of a body couple, you will not have tau ij is equal to tau ji, but normally we write tau ij equal to tau ji for fluids. The reason is fluids will normally not sustain body couples, but if fluids contain particulate type of matters, like if the fluids contain engulfed particles which by virtue of their own rotation can introduce body couple in the fluid, then it is possible that the the equation of motion for the fluid has to be written by taking the body couple into account, and that kind of fluid is there in the study of fluid mechanics, and that type of fluid, one such example is micropolar fluid. So, we will not be discussing about micropolar fluids in details, because I mean we do not have enough scope in this fundamental course to talk about that, but these are special types of fluids, you know, which can sustain couple body couples. So, it is possible that for such a fluid you do not have tau ij is equal to tau ji, and you write separate differential equations for angular momentum conservation. Just like we write differential equations for linear momentum conservation, we need to write separate differential equations for angular momentum conservation. Now, micropolar fluids are very much important in the context of microfluidics research, because there are certain examples when micropolar fluids are used to model some biological fluids. Like for example, there are instances when micropolar fluids have been used to model blood, and you know biological fluids are very important in microfluidic applications. Therefore, I mean we cannot rule out those possibilities where you will have tau ij is not equal to tau ji, but if the fluid is not sustaining any body couple, it is true that tau ij is equal to tau ji, and we will consider that kind of example for the remaining part of this course. Now, maybe for a little bit of the remaining part of the exercise, we will go to the board and do it, because some of the algebra is little bit involved and that is not worked out in details in the slides. So, what we will do is that, as I told you earlier, that we will like switch over from the board to the slide whenever necessary, and for some detailed working out we will use the board rather than the slide. So, let us say that what formalism we have come across is that we have surface force, we have body force. The surface force we are writing in terms of what? So, the ith component of the surface force, what we are doing, if we have a control volume like this, you consider a small area dA, the surface force per unit area is Ti along the ith direction, and that you multiply with dA and integrate this over the entire control surface. This is what we do, right. So, now this Ti, what we can write? We can write as, the Cauchy's theorem gives it tau ji into eta j, but from angular momentum conservation, since tau ji equal to tau ij, we can write this as tau ij eta j dA. Now, we will try to express this in terms of dot product of two vectors. Why we are interested to express this in terms of dot product of two vectors is because we can then express it in terms of a volume integral by using the divergence theorem. That is what is our motivation. See, I will try to give you a big picture. In all the derivations using Reynolds transport theorem, we have some surface integrals and some volume integrals. You will find that the terms in the Reynolds transport theorem in general, forget about the complexity, at the end it will be either surface integral or volume integral. Now, to derive the differential equation from the integral form, what we do? We convert the surface integral into volume integral by using the divergence theorem. So, the first requirement is express the surface integral in terms of a dot product, so that we will be in a position to convert it into volume integral. Then all terms will be converted into volume integral, and you will get integral of something into dV equal to 0. Because that dV, the choice of the control volume is arbitrary, so that something, integral of which is 0, that something is 0, that will give rise to the differential equation. So, that is the basic philosophy by which you derive the differential form of the conservation equation from the integral form of the conservation equation. So, we will be expressing this in terms of what? We will be expressing this in terms of a dot product. So, what we do is that, see, let us maybe use a different color to highlight this. So, what this is? So, this is tau I1 eta 1 plus tau I2 eta 2 plus tau I3 eta 3, right. So, that expression, this one, we can write tau I1 into I cap plus tau I2 into j cap plus tau I3 into k cap dot eta 1 I cap plus eta 2 j cap plus eta 3 k cap, where I, j, k are unit vectors along x, y, z. Okay. So, what we do out of here, we you can see that this is essentially a vector, right. It has its three components, tau I1, tau I2, tau I3 as just some numbers, scalar components. So, let us give it this vector a name tau I, this is just a name that we give. Often in the books, in some books this is called as stress vector, just a name given. So, and this is what? This is the unit vector eta, with its 3 components. So, this integral is nothing but integral of what? Tau I dot eta dA. So, this is nothing but divergence of tau I dV. Okay. This integral is over what? The volume that bounds the control surface. The volume, rather the control surface is the surface that bounds the control volume. So, this is the control volume. So, we have got the surface force, the body force. So, the surface force we have written in terms of what? The surface force we have written in terms of a volume integral. The body force anyway is normally written in terms of the volume integral. So, the body force, if Bi is the body force per unit volume along I. So, what is Bi? Small Bi is the body force per unit volume along I. So, if you just multiply it with dV and integrate it over the control volume, then this is the surface force. So, by these two we have represented the surface force and the body force. So, we have represented the force in the Reynolds transport theorem for linear momentum conservation. Let us recollect. So, maybe let us go through the slides so that we can go a little bit quickly, because we have already represented the forces, the remaining part is trivial. So, if you look here, the resultant force acting on the control volume, we have just shown in the board how to do the Reynolds, how to find out the resultant force acting on the control volume. So, the resultant force, now the right hand side is like this is the change within the control volume, the first term, and this is the outflow minus inflow term. So, here again it was the surface integral or area integral, we have converted it into volume integral. So, that is how this, the last term in the right hand side is divergence of rho ui into v. What is ui? Ui is the ith component of the velocity v. V is the velocity vector, its ith component is ui. So, you have divergence of rho ui v dv. So, how has this term come? Let us quickly look into the board and figure out that how this particular term has come. Let us switch over to the board. So, you have this particular term is equal to what? Rho ui is small n, that is capital N is m into ui, per unit mass is ui. This is the last term, outflow minus inflow term. This v is v relative, but we have considered the control volume to be stationary, so that the relative velocity is same as the absolute velocity. So, here the vector field F is nothing but rho ui into v. Okay. So, this for the control surface is as good as integral of divergence of rho ui v dv. Okay. So, that is very straightforward, this is using the divergence theorem. Let us get back to the slides. So, as you see here that so the right hand side we have written in terms of the volume integral, left hand side is also written in terms of the volume integral, because both the forces are expressed in terms of the volume integral.